Welcome to the fourth lecture of this week. Today we will discuss about higher order shear deformation theories. So far we have discussed about, we have analyzed using the assumption that there is no shear deformation, and then we relax the assumption and we assume that there is shear deformation, but that is first order, and then we will go for higher order. So, if we just look back quickly, our initial assumption was the bend shape of a plate. If I view from one side, it looks like this, and the angle which was initially 90 remains 90. And if I draw a line, if I draw a tangent here, and if I take the angle with respect to the horizontal axis, say x, and this is z. So, this is del w by del x, and then we saw that this angle is also del w by del x. Now, here this plane which was initially plane before bending remains plane after bending also. Then our next development was it still remains plane after bending, but that angle 90 degree is not preserved. So, it can change to something else. So, that brings us one more variable in our solution. So, a bend shape can look like this. So, here if I this is del w by del x, and this angle is something psi x, this is x and this is z. Now, this psi x we defined with respect to y axis. So, we have x y z. So, psi x is positive in this direction. That means, in this case psi has negative sign incorporated. So, here the assumption was u is equal to u0 minus del w by del x, and here it is u is equal to u0 plus z into psi x. So, I am doing it only for a section if I view it along y direction, that means in the xz plane. Now, here we relaxed one assumption. So, this 90 degree no more remains preserved, but still this plane after bending remains plane, and because of that our shear stress remains constant throughout the thickness. So, no shear strain, and here we have along no shear strain gamma xz, gamma yz, gamma xy can be there, and here gamma xz, gamma yz constant along z. Now, if I further relax the assumption and make the model little bit more involved, then I can get the deflected shape where the plane section does not remain plane before and after bending. So, if I draw it, a section can look like this. And again, so in this case our assumption is it is x, this is z. In this case our assumption is u, a function of x y z, is equal to u0 function of x y plus z into psi x, a function of x y, plus we have two more terms plus z square into xi x, which is a function of x y, plus z cube multiplied by zeta x, which is a function of x y. So, here because of these terms we can see that this u 0 can vary along the I mean can vary non-linearly along z. So, that is why a section which was initially plane after deformation can become a curve. Now, because of this relaxation of the assumption, this model itself can incorporate the fact that shear strain is 0 here and 0 here. So, this does not so here the shear strain gamma x y and gamma y z and gamma x z need not be constant along z. So, gamma x z, gamma y z are not constant along z. In the previous case which we discussed in the last lecture, here because gamma x z and gamma y z was constant, so that gives some kind of non-physical behavior, because we know that gamma x z and gamma y z should be 0 at the top and bottom. So, that is why there was a need for shear correction factor. For to ensure energy equivalence, but here shear correction factor is not needed, because this model can itself ensure that gamma y z and gamma x z are 0 at the top and bottom, and it can vary the way it should along z. Correction factor not needed. So, this model we call it classical laminate theory CLT, and this is based on the Kirchhoff theory. So, in plate theory we call it as the Kirchhoff theory. We can say that it is a 2D version of Euler-Bernoulli beam which does not allow shear deformation, and this comes from Mindlin Reisner theory, which allows for shear deformation, but variation is linear, shear strain is linear along z, and this is higher order theory. Now, there is not one higher order theory, there is various higher order theories. So, we will just talk one of them which assumes it to be like this. Now, let us look into its formulation. So, we have already talked about the kinematic assumption. So, this is our kinematic assumption or kinematic consideration. Now, with that let us do the development. So, first we will look at strain displacement relationship. Strain displacement relationship. So, the strain displacement relationship, as we know, okay, before doing that, it is better that we satisfy the condition that shear is 0 at the top and bottom, shear strain is 0, and reduce the model, and then based on that we can do it. So, before looking into all the shear strain displacement relationships, let us first just look into gamma x y z and gamma x z. So, gamma x z before that let us just write the relationship once more. So, kinematic considerations are along for u 0 we have u 0 as a function of x y z is equal to u as a function of x y z is equal to u 0 as a function of x y z plus we have z into psi x. So, this is only x y, no z is there, plus we have z square into xi x as a function of x y plus we have z cube zeta x as a function of x y. Similarly, V, the displacement along y direction is V 0, which is which we can call as mid plane displacement plus z into xi y as a function of x y. So, up to this and this and this, it is same as what we discussed in the last week, the first order shear deformation, and then we have the higher order parameters xi y as a function of x y plus z square into xi y plus z cube into zeta y. Based on this, if we try to define gamma x z, that becomes del u by del z plus del w by del x. So, w as a function of x y z remains w as a function of only x and y. So, w is not z dependent, that assumption is still there. So, there is no thickening or thinning of the plates. Now, that is gamma x z, and so that we can define as, if I just differentiate this entire thing in with respect to z, it becomes psi x as a function of x y plus 2 z into xi x plus 3 z square into zeta x as a function of x y. Now, by satisfying the condition that at the top of the laminate and at the bottom of the laminate shear strain are 0, we can get rid of one of the variables here. So, let us see that. So, let us assume that our laminated plate has a thickness h. So, this is h by 2, this is h by 2. So, the z coordinate of this is h by 2 and z coordinate of this is minus h by 2. So, here we have z equal to 0 and we know this is z 0, this is z 1 and we have all the way up to z n. So, z 0 is equal to minus h by 2 and z n is equal to h by 2. And also for the time being, let us assume that x and y coincides with 1 and 2. So, assume x y coincide with 1 2 and 1 2 are the, as we know, these are the principal material directions. That means, fibers are along 1 and the direction perpendicular to it in the in plane is 2. So, we have x that coincides with 1, y coincides with 2 and accordingly we can say a z that always coincide with the third direction 3. Now, so we can write tau y 3, that means tau 1 3, and that also we can call as tau x z because 1 and x and 3 as z are coincident, that is equal to g 1 3 shear modulus multiplied by gamma 1 3, which is same as g 1 3 multiplied by gamma x z, and gamma x z is this. So, at the top and bottom we can write. So, let us just complete this. So, this is g 1 3 multiplied by psi x plus 2z into xi x plus 3z square into zeta x. Now, at Zn is equal to h by 2, we can write tau 13 is equal to tau xz is equal to 0, and that is equal to psi x plus 2 multiplied by h by 2 into xi x plus 3 multiplied by h square by 4 into zeta x, and entire thing is multiplied by G13. Similarly, we can say that at Z0, which is minus h by 2, here z h by 2 we have tau 13 is equal to tau xz is equal to 0 is equal to sigma x minus 2 into h by 2, which is h xi x plus 3 into h square by 4 into these are y. Now, we are looking at fine, we are looking at x only. So, and G13. So, let us call it equation number 1, let us call it equation number 2. Now, if I subtract 2 from 1, this gives us that xi x is equal to 0. So, one variable we do not have to bother now, and we still have u0 v0 w, psi x psi y and zeta x zeta y. Now, if we add up 1 and 2, if I do 1 plus 2, then we can express this zeta x in terms of psi x and xi x. Okay, w is should also have been here, because sorry about it. So, when we if I write the complete expression, del w by del x was missing here. So, del w by del x, and similarly here also we should have plus del w by del x, and if I just add this up here. So, we have del w by del x into G13, and here also we have del w by del x. So, plus del w by del x multiplied by G13. So, this because of this we should have this also, and that was missing somehow. So, but still the conclusion xi x is equal to 0 remains valid. Now, if I do 1 plus 2, then we can add these two equations up, and from that sum we can express xi x using the other variables psi x and w. So, if I do that, we get xi x is equal to minus of 4 del w by del x plus psi x and divided by 3h square. So, with this we can reduce the number of unknowns. Now, during this proof we had to assume that x y coincides with 1 and 2, because that makes this proof easier. Otherwise, we would have the dependence of tau xz on gamma yz also, similarly dependence of tau yz on gamma xz also. That is not a problem, we could have done that with the generic with that generic formulation also, but here just for the sake of easiness we did it in the principal material direction, and the conclusion remains valid. Now, similarly we can write xi y is equal to 0 and we can say that zeta y is equal to minus 4 into del w by del y plus psi y divided by 3 h square, and this comes from the fact that tau y z is equal to 0 at z is equal to z n, which is h by 2, and z is equal to z 0, which is minus h by 2. So, now with all these we can write the new formulation as u 0 as a function of x y z is u 0. So, u as a function of x y z is u 0 plus z psi x multiplied by z, and then xi is not there, and then we have minus 4 by 3 h square del w x by psi x. Similarly, v becomes v 0 plus z into psi y minus 4 by 3 h square del w by del y plus psi y. So, this becomes our new kinematic assumption or formulation. So, this automatically satisfies that gamma y z and gamma x z are 0 at the top and bottom, and because of this we do not need to have any shear correction factor because of this provision. So, now let us write the full strain displacement relationship. So, here it is z cube and z cube. So, now let us write the strain displacement relationships. So, we know epsilon x, which we denote as epsilon x here. So, that is del u by del x, and that comes out to be epsilon x 0 plus z into kappa x with superscript 0 plus z cube into kappa x with superscript 2, and we will define these terms. Similarly, epsilon y comes out to be epsilon y comes out to be del v by del y, which is epsilon y 0 plus z into kappa y with superscript 0 plus z cube into kappa y with superscript 2. So, these are not squares, rather they are superscripts, and then we have epsilon zz is 0, and then we have epsilon xy gamma xy rather, the engineering shear strain in the xy plane, which we denote as epsilon s, and that is equal to del u by del y plus del v by del x, and that becomes epsilon s 0 plus z into kappa s with superscript 0 plus z cube into kappa s with superscript 2, and then we have gamma x z, which this we can write as gamma x z 0 plus if we just, so that is that will come from differentiating this quantity. So, plus z square kappa s 2 and gamma y z, and that is equal to del u by del z plus del w by del x, and gamma y z comes from del v by del z plus del w by del y, and that comes out to be gamma yz 0 plus z square multiplied by kappa, okay, please excuse me, these are not kappa s, kappa rather xz and yz. So, xz yz with superscript 2. So, now we will see what these individual terms are, epsilon x 0 y 0 s 0 and these kappas. So, where epsilon x 0 is del u 0 by del x, epsilon y 0 is del v 0 by del y, del u 0 by del y plus del v 0 by del x. These are all known to us. And then we have kappa s 0 terms, this also we know. So, here it is del psi x by del x, kappa, this is kappa x 0 and kappa y 0 is del psi y by del y and kappa s 0 is del psi x by del y plus del psi y by del x. Then comes the higher order kappas. So, del x, k x kappa x 2, and that is, those are the new terms in this theory. So, that is minus 4 by h square, and then we have we should have minus 4 by minus 4 by h 3 h square multiplied by del psi x by del x plus del 2 w x by del x 2, and then we have kappa y with with 2, and that is minus 4 by 3 h square into del 2 psi y by del y plus del 2 w by del y 2, and then we have kappa s 2, and that is minus 3 by minus 4 by 3 h square multiplied by del psi x by del y plus del psi y by del x plus 2 into del 2 w del x del y, and then we have kappa x z 2 and kappa y z 2, and because before that let us define gamma x z 0, and that we have seen as that we can get from this quantity. So, we just differentiate this with respect to z. So, that will give us minus 4 by h square del w x by psi x. So, del w x by psi x, and similarly kappa y z 2 becomes minus 4 by h square into del w y by del w by del y plus psi y. So, this is how the strain displacement relationship will look if we incorporate this shear deformation theory. So, here these are the new insertions, these terms, this term, and similarly this and this as compared to our previous considerations, and that gives us nonlinear terms in z, and those we have defined here. So, this brings us to the end of this lecture. In the next class we will find out the laminate stiffnesses and governing differential equations based on these considerations. Thank you.